Okay, so the goal of this video is to talk about divisibility in f bracket x, and in particular talk about some of the parallels between f bracket x and z. We'll see that polynomials whose coefficients come from a field behave very similar to the integers in a lot of ways, and we'll explore this a little bit further as we study rings in the coming lectures. Okay, so here's how we start. We're going to assume throughout this entire video that f is a field, capital F is a field. And first we'll talk about what it means for a polynomial to divide another polynomial. And we already have the integers as a motivation for our definition. So what I'm going to do is I'll take two polynomials, a of x and b of x, and assume that b is non-zero. And what I want to define is a divided by b. So I want to define what it means to take b of x and divide a of x by it. So we'll use our definition from the integers. We'll say b of x divides a of x if there exists a polynomial c of x in f bracket x such that a is equal to b times c. So a of x is equal to b of x times c of x, and we'll use our usual notation of b of x divides a of x. Okay, so same notation, same type of definition. We've just replaced our z with f bracket x. And you will see that throughout this video that this happens with a lot of our theorems. So we're going to see that f bracket x, a lot of the theorems are going to look familiar because they're the same theorem that held for z. Okay. So let's look at some examples of this. Our first example is in q bracket x. We have that x squared minus 1 divides 2x to the fourth minus 2. Why? Well, 2x to the fourth minus 2 can be written as x squared minus 1 times 2x squared plus 2. Okay, so this is our first example. We might also notice that any multiple of x squared minus 1 is going to divide 2x to the fourth minus 2. For example, if I take 5x squared minus 5, that's also going to divide 2x to the fourth minus 2. And let's kind of look at this. We have 2x to the fourth minus 2 is equal to 5x squared minus 5 times 2/5 x squared plus 2/5. So in some sense, what have I done? I've introduced a factor of 5 over here at the expense of introducing a factor of 1/5 over here. And we'll keep this idea in mind because we'll need this for a proof in a minute. Okay, so these are two examples in q bracket x. And finally, what about some different fields like z7? So in z7 bracket x, here's kind of an interesting one. We have 3x plus 1 divides 4x squared plus 5. And why is that the case? Well, 4x squared plus 5 can be written as 3x plus 1 times 6x plus 5. So let's take a look at this. 3x times 6x is 18x squared, and 18x squared mod 7 is going to give us 4x squared because 18 and 4 are the same mod 7. Then I have 6x plus 15x, that's going to give us a 21x, but 21 is the same as 0 mod 7. And then finally, 1 times 5 is 5, so that gives me this 5 right here. Okay, so we're ready to prove our first basic theorem. So we'll start with two polynomials a of x and b of x in f bracket x, and we'll start with a constant c. It'll be a non-zero constant. And the first part of our theorem says that if b divides a, then c times b of x divides a of x. Okay, so the second part of our theorem says if b of x divides a of x, then the degree of b of x is less than or equal to the degree of a of x. So let's prove these. Well, before we prove them, let's kind of observe something. So in Z, we had this theorem in, I think, our very first video or second video, something like that, that if b divides a, then negative b divides a, right? In this theorem, we have if b divides a, then any constant multiple from my field of b is going to divide a. So in some sense, these constants are going to play the role of 1 or negative 1 for us when we're working in Z bracket x. We also have if b divides a, then the degree of b is less than or equal to the degree of a. That kind of looks like the fact if b divides a, then the absolute value of b is less than or equal to the absolute value of a. And this isn't a coincidence. We'll see in the coming lectures that this isn't actually a coincidence. Okay, so let's get to the proof of this. The proof is rather straightforward, and it uses an idea we just mentioned in our example, right? So let's prove the first one. So actually, before we begin, I'll just say, suppose that b of x divides a of x, right? So then we can say that there exists some polynomial, let's call it, I don't know, let's call it t of x in f bracket x, such that a of x is equal to b of x times t of x. Okay, so what can we do with this? Let's prove one. Well, I know that a of x can be written as b of x times t of x. And what I'm going to do is I'm going to use the common trick that's used in a lot of proofs. I'm going to multiply by 1. So I'm going to multiply by c times c inverse times b of x times t of x. And then what I'm going to do is I'm going to take the c and leave it here with the b. So I have c times b of x, and take the c inverse and attach it to the t, right? So I could say hence c times b of x divides a of x, since, well, what have I done? This polynomial I've created, c inverse t of x, it has coefficients in f bracket x, right? It's a polynomial t of x, it has coefficients in f bracket x, and I'm just multiplying them by all, rather, it has coefficients in f, and I'm multiplying each of those coefficients by another element of f. So this guy is in f bracket x. Okay, and I'm done. Great. So it's kind of like when we did this proof for z and we multiplied both b and t by -1, right? We wrote a is equal to b times t, which is equal to negative b times negative t. Okay, so same idea. What about the second one? Well, the second one's also pretty straightforward. I know that the degree of b of x is less than or equal to the degree of b of x times t of x, which is equal to the degree of a of x. Okay, and that finishes my proof. So an important type of polynomial that's going to arise for us is what's called a monic polynomial. And a monic polynomial is just a polynomial whose highest degree term has coefficient 1. So its leading coefficient is 1. So let's look at some examples. Our first example is 2x cubed plus 3x squared plus 1. I see that the leading coefficient here is 2. So this is an example of a polynomial that's not monic. I just look at the highest degree term and I look at its coefficient. If it's not 1, the polynomial is not monic. I can also look at this example, x to the 7th plus 6x to the 5th plus 9x squared plus 1 in Z7 bracket x. And then I look at its highest degree term, it's x to the 7th. The coefficient here is 1. So this is a monic polynomial. So monic polynomials, again, highest degree term has a coefficient of 1. That's all that means. Okay, so now we're ready to define the notion of greatest common divisor of two polynomials. And the idea is we're just going to follow our definitions from the integers and see how far we can push things. We're going to see that things can actually be pushed pretty far. So we're going to start with two polynomials, a of x and b of x, and we'll assume that they're not both 0. So the idea is that one of them is allowed to be 0 as long as not both of them are 0. Okay, so what does it mean to be a greatest common divisor? So we're going to say a monic polynomial, d of x in f bracket x, is called the greatest common divisor of a of x and b of x if, well, first, d of x has to divide a and d of x has to divide b. And now the question you might ask is, well, why are we assuming the polynomial is monic? Well, we just showed that a multiple of a divisor is always a divisor. So if I want to use this article the, if I want to make sure that this greatest common divisor or GCD is going to be unique, I need to assume that this thing is going to be monic. We'll see that that's kind of what holds it together. The point is that if your field is infinite, for example, and you don't assume your greatest common divisor is monic, you're going to have infinitely many polynomials that are going to satisfy part 1 of this definition and part 2 of this definition, because any multiple of a GCD will also be a GCD. Okay, so that's why the word monic is used. It ensures uniqueness, which we still have to prove. We don't know uniqueness. We have to prove this in a second. And 2, we're going to say if c of x is any other common divisor of a and b, we want to somehow say that c is less than d. And the only way we can really do that is to say that the degree of c is less than or equal to the degree of d, right? So we're going to say that the degree of c is less than or equal to the degree of d. Okay, so this is our definition of greatest common divisor. We're going to show that, again, this is the appropriate article to use here, that this is actually a unique polynomial. But first, we have to actually show that greatest common divisors even exist. How do I even know that there are common divisors? Well, this is actually kind of simple because 1 always divides a of x and b of x, right? A of x can be written as 1 times a of x, b of x can be written as 1 times b of x. So 1 always divides any two polynomials. Okay, so let's now prove that greatest common divisors are always unique and see how they parallel greatest common divisors from the integers. Okay, so our first theorem will look pretty familiar. So we're going to say let a of x and b of x be two polynomials in f bracket x that are not both 0. Then the GCD d of x in f bracket x of a of x and b of x is unique. And moreover, there exist polynomials u and v in f bracket x such that d is equal to au plus bv. right? So D can be written as a polynomial linear combination of A and B. Okay, so this is exactly the same theorem we had in Z, except instead of elements in f bracket x, we had elements in Z. And we're going to see that the proof is actually identical for the most part. We're going to see a lot of these proofs are pretty much the same as the proofs that we did in Z. The only thing that is a little bit different is going to be the uniqueness portion. So we'll go through all the details, but the uniqueness portion is going to be a little bit different. But first, let's prove that we can actually write GCD as a linear combination. Okay, so what I'm going to do is I'm going to start with this set of elements am plus bn. So I'm going to suppress the of x notation just for visual clarity. So instead of a of x, I'm going to write a. Instead of b of x, I'm going to write b. But everything here is polynomials. So I'm going to consider the set of elements am plus bn, where m and n are polynomials in f bracket x. And the first thing I'm going to note is that S is not the empty set, since a times 1 plus b times 0 is an element of S, right? So this set is non-empty. So what I'm then going to do is I'm going to consider all of the monic polynomials inside of S. I know if a polynomial is inside of S, so is any multiple of that polynomial. So I could always turn any polynomial in S into a monic polynomial. And I'm going to consider all of the monic polynomials inside of S, and I'm going to pick one of those polynomials of smallest degree. So I'm going to call this polynomial t. So t is going to be a monic polynomial in S of smallest possible degree, and I'm going to write t as au plus bv, where u and v are polynomials in f bracket x, right? The set is non-empty, so I know by well ordering there is a smallest degree polynomial in there, and moreover, since a scalar multiple of a polynomial is always a polynomial, since I could take any polynomial and multiply it by any element of f, I could turn any smallest degree polynomial into a monic polynomial, if you will. Okay, so my first claim is going to be that t is a greatest common divisor of a and b. So this thing I've created, this au plus bv of smallest degree, which is monic, I'm going to show that this is a greatest common divisor, and then I'll go on and show that this is unique. Okay, so the first thing I need to show is that it's actually a common divisor. I need to show that t divides a and t divides b. Okay, so let's prove this. Well, how do I go about doing this? Well, by the division algorithm, which we just proved in the last video, there exists polynomials, let's say q and r, in f bracket x. So again, I'm suppressing the of x notation just for visual clarity, such that a is equal to tq plus r. And moreover, I either have the degree of t, or rather the degree of r is less than the degree of t, or r is equal to 0. All right, those are my two options. That's what my division algorithm tells me. Okay, my goal is to show that r is equal to 0. If I want to show t divides a, I want to show that there's a remainder of 0. Okay, so how do we do this? Well, if a is equal to tq plus r, I can then write r is equal to a minus tq. And what I'm going to do is I'm going to substitute my expression for t. I know t can be written as au plus bv, so I'm going to write this as a minus au plus bv times q. And what is this going to leave me with? Well, if I rewrite this, this is going to be a times 1 minus uq plus b times negative vq. And I might notice that 1 minus uq is a polynomial, negative vq is a polynomial. So what do I have? I have that r is a times a polynomial plus b times a polynomial. So r must be an element of S, right? So I could take m to be 1 minus uq and n to be negative vq, and I see that r is an element of S. Okay, but we have a small problem. We know that t is the smallest degree polynomial in S, and I have that the degree of r is smaller, right? So by minimality of t, we know that the only possibility is that r is equal to 0, and hence we have that a is equal to tq, right? The idea being that if r is non-zero, then the degree of r is less than the degree of t, and then I could just rescale r. I could multiply r by some element to turn it into a monic polynomial inside of S, which is smaller than t in degree, right? So the only possibility is that r is 0, and hence a is equal to tq. In other words, t divides a, right? And then I could say similarly, an identical argument gives me that t divides b. Okay, so I've shown that t divides a and t divides b. That's the first part of my definition of GCD. Okay, so now let C be any common divisor of A and B. So C is in f bracket x and C divides A and C divides B. What I'd like to show is that the degree of C is less than or equal to the degree of T, right? I'm trying to show that T is the GCD, so I have to check the second condition. Well, what can I say? I can say there exist polynomials, let's call them f and g, in f bracket x, such that, well, A is equal to CF and B is equal to CG. All right, so now let's use this fact in our expression for T. So I could say then T is equal to, well, we know it's equal to AU plus BV. I can now write this as CFU plus CGV, which is equal to C times FU plus GV. In other words, C divides T. In other words, the degree of C is less than or equal to the degree of T by the theorem we just proved earlier. Okay, so that finishes our proof that the GCD or a GCD can be written in terms of A and B. Now we're going to show that T is actually the unique GCD. Okay, so now we'll show that T is actually the unique GCD of A and B. Okay, so how do we do this? Well, we assume that there's another GCD. So we'll say let D be another GCD. And we know by 2, since D and T are both common divisors of A and B, I know that D has to divide T and T has to divide D. So I know that D and T have to have the same degree. Moreover, since D is a GCD, I know that D has to divide A and D has to divide B. So I can write A is equal to DF and B is equal to DG for some F and G in F bracket X. Okay, so what do we have? Well, then I can take T, I can write this as AU plus BV, which is now DFU plus DGV, which is equal to D times FU plus GV. All right, and now the idea is that T and D have the same degree, so the degree of this guy has to be 0. The degree of FU plus GV has to be 0. So the degree of FU plus GV is equal to 0. In other words, FU plus GV is equal to a constant, and this constant is some non-zero field element, right? So FU plus GV has to be a constant. And now the idea is since D and T are monic, well, their leading coefficients have to be 1, so that means C is going to have to be 1, because if I were to take D and multiply it by a non-1 scalar, a scalar that's not 1, T would no longer be monic, right? Since D and T are monic, we have that C is equal to 1. In other words, that T is equal to D. Okay, and that finishes the proof of uniqueness. Okay, so now we can continue with some of our parallels. So on the left-hand side, at the top here, I've rewritten the definition of GCD. So just to recall, if A and B are two polynomials that are not both 0, a monic polynomial D of x and f bracket x is the greatest common divisor, or the GCD of A and B, if D divides A and D divides B, so it's a common divisor of A and B, and if C is any other polynomial such that C divides A and C divides B, then the degree of C is less than or equal to the degree of D. Okay, what I claim is that this degree of C less than or equal to the degree of D condition can be replaced. So just like with the integers, we're going to replace it with some other condition, or we're going to be able to replace it with some other condition. So we're going to say, again, A and B are two polynomials that are not both 0. So one of them is allowed to be 0 as long as not both of them are 0. We're going to say a monic polynomial D of x is the GCD of A and B if and only if condition alpha, that D divides A and D divides B, is satisfied, and condition beta, if C is a polynomial such that C divides A and C divides B, then C divides D. So in some sense, I could take this less than or equal to condition and replace it by a divisibility condition. Okay, so let's prove this theorem. Again, this looks very, very similar to the integers, and we'll see that the proof is identical to the proof that we did in the integers. The only thing that changes is that C less than D gets replaced, or C less than or equal to D gets replaced with the degree of C is less than or equal to the degree of D, right? So a lot of these proofs are going to look exactly the same as the proofs that we did in the integers in some earlier videos. Okay, so let's let's prove the forward direction. So I'll say, suppose D is the GCD. So I'll just write D instead of D of X, is the GCD of A and B. Well, by definition, so we know we have alpha because 1 is satisfied. So since 1 is satisfied. Okay, so we know that 1 is satisfied. Well, what else do we know? We know by our last theorem that D can be written as AU plus BV for some polynomials. Let's call, U and V in f bracket x. Okay, so that's our last theorem that we just proved. D can be written as AU plus BV. What I'm going to do is I'll suppose that C is an f bracket x, and C divides A, and C divides B. Okay, well, then from earlier, it's going to look like the last proof. I know that A can be written as CF, and B can be written as CG for some F and G in f bracket x, right? So what do we have now? We have then that D is equal to AU plus BV, which can now be written as CFU plus CGV, which is equal to C times FU plus GV. In other words, C divides D. Okay, so beta is satisfied. Okay, so we have that if D is the GCD, then we automatically get conditions alpha and beta. Okay, so the backwards direction is a lot easier. We're going to suppose that D is monic, and D satisfies conditions alpha and beta, and we might notice right away that alpha and 1 are the same thing. So we have that, hence, D satisfies condition 1. Right? And now what I'm going to do is I'm going to say let C be some polynomial in f bracket x such that C divides A and C divides B. Okay, well, what do I know? By beta, we know that C divides D, and then by an earlier theorem, so by an earlier result, we know that the degree of C is now less than or equal to the degree of D. Okay, so we've proved our theorem. We've proved the other direction. So this gives us a way of recharacterizing the notion of GCD. It removes this dependency on inequalities and gives us a divisibility condition instead. So we have one more theorem that is going to look like a theorem we saw when we were studying the integers. So we'll take A of x, B of x, and C of x to be polynomials in f bracket x, and suppose that A divides BC, and that the GCD of A of x and B of x is 1. So we'll assume that A of x and B of x are relatively prime. Then we have that A of x divides C of x. Okay, so let's start our proof. So we know that there exist polynomials. Let's see. We're going to have a U of x, a V of x, and another polynomial we'll call f of x, such that two things hold. Since the GCD of A and B is 1, I can write A of x times U of x plus B of x times V of x is equal to 1. And since I know A divides BC, I can write B of x times C of x is equal to A of x times F of x. All right, so I have something that looks like this. And let's put these two together. Well, since I know A of x, U of x plus B of x times V of x is equal to 1, I can multiply both sides of that equation by C. So I'm going to get C of x is equal to C of x times A of x times U of x. And now you can see why I'm suppressing the of x's when I write these things, times C, plus C of x times B of x times V of x. And I know that B times C can be replaced by A times F, right? So BC can be replaced by AF. So I'm going to replace this BC right here. So let's do that. This is going to be C of x times A of x times U of x plus A of x times F of x times V of x. And then what I'm going to do is I'm going to factor an A out from both of these. And remember, we're working over a field, so all of our multiplication in f bracket x is commutative. So I can factor out this A of x, and I'll get c of x times u of x plus f of x times v of x. And so what do we see? We see that a of x has to divide c of x. Okay, so this is just another theorem to show how much the polynomials parallel the integers. Not only are the theorems the same, but the proofs of the theorems are pretty much identical. So our goal for the remainder of this video is going to be to define and talk about the properties of something like a prime polynomial. So we know in the integers, there's this notion of prime number. These are numbers that are divisible by, these are numbers p that are divisible by plus minus 1 and plus minus p only. And so we'd like to define something similar in polynomial rings. So what are we going to do? Well, first we need to define what's called an associate, so we can capture this kind of plus minus 1 plus minus p behavior. So we'll say the following. We'll let R be a commutative ring with identity. So 1R is the identity. And we call A and B associates if there exists a unit U such that A times U is equal to B. So we'll say A and B are associates in that case. One thing you might notice is that this can also be written as A is equal to B times U inverse. So what are some examples of this? Well, 2 and negative 2 are associates in Z. Why is that the case? Well, negative 2 is equal to 2 times negative 1, and we know that negative 1 is a unit in Z. The only units in Z are 1 and negative 1. I know x squared plus 1 and 3x squared plus 3 are associates in Q. Why? Because 3x squared plus 3 is just 3 times x squared plus 1, and I know that 3 is a unit in Q. 3 is an element that's invertible under multiplication. Another thing I can write is that if U and V are units in my ring, then they're automatically associates. Why is that the case? Well, I can write U as V times V inverse U, and I'll notice that V inverse U is going to be a unit. Why? Well, V inverse U times U inverse V is going to equal 1. Okay, so these are going to be what are called associates, and now we're finally ready to define what we're going to call an irreducible polynomial. So this is going to play the same role for us that prime numbers played in the integers. So let's do that. Okay, so let's define the notion of an irreducible polynomial. So an irreducible polynomial is a polynomial whose only divisors are units and associates. So let's kind of think about what this means and if this matches up with our definition for integers. The one thing to remember is a prime integer, p, is one whose only divisors are plus minus 1 and plus minus p. So the plus minus 1 are units, the plus minus p are associates of p. Right. So in the integers, we had a similar notion that we called something prime if its only divisors were plus minus 1 and plus minus p. So here we're going to say that a polynomial is irreducible if its only divisors are units. In this case, our units are just scalars, right, or just elements of our field, and associates are just going to be unit multiples of p. Okay, so let's look at a quick example, right? We're going to have a bunch of theorems that are going to help us determine whether or not a polynomial is irreducible. You might also remember that an irreducible polynomial, if you think back to courses you might have had in the past, like high school algebra or something, you might have said, wait, a polynomial is irreducible if it can't be factored into lower degree polynomials. And now you're telling me irreducible means something else. We'll see that that notion is actually equivalent to our definition in a second. So let's look at an example. So first, I'm going to show that 2x plus 5 is irreducible. So let's suppose I have a divisor. So suppose I have a polynomial f of x, and f of x divides 2x plus 5. Right? What do I know from that? Well, then I know that the degree of f of x must be less than or equal to the degree of 2x plus 5, which is 1. Okay, and moreover, I know that there exists some polynomial g of x in f bracket x such that 2x plus 5 is equal to f of x times g of x. Okay, so what are my possibilities? My possibilities are 1, the degree of f of x is equal to 0. In other words, f of x is a non-zero constant, so f of x is a unit. And 2, the other possibility is that the degree of f of x is equal to 1. But then if I look at this equation that I have here, if the degree of f of x is 1, and I have a degree 1 polynomial on this side, that means that the degree of g of x must be 0. So this implies that the degree of g of x is 0, which implies that g of x is a unit. And what does that tell me? That implies that f of x is an associate of 2x plus 5, right? I've shown that 2x plus 5 is equal to f of x times a unit. Okay, so I have that 2x plus 5 is irreducible in R bracket x. Okay, so finally we're ready to prove the theorem that I kind of mentioned a minute ago that we'd suspect all along. So we'll call a polynomial reducible if it's not irreducible. And the idea is going to be that a polynomial is reducible if and only if it can be written as a product of smaller degree polynomials, in particular, 2 smaller degree polynomials. Okay, so let's prove our theorem. So let's prove the forward direction. So I'll say, suppose f of x is reducible. Well, what does that tell me? That tells me that then there exist polynomials g of x and h of x in f bracket x such that f of x is equal to g of x times h of x, and neither of them are constant. So I'll say that the degree of g of x is bigger than or equal to 1, and the degree of h of x is bigger than or equal to 1. Right? Constant polynomials have degree 0. If a polynomial is reducible, then I can write it as a non-constant polynomial times a non-constant polynomial. So these two polynomials have to have degree bigger than or equal to 1. But we now might notice that the degrees of these two polynomials, g and h, have to add up to the degree of f. Right? So, but then we have that the degree of g of x has to be strictly less than the degree of f of x, and the degree of h of x has to be strictly less than the degree of f of x, right? If any of them equal the degree of f of x, then the degree on the right-hand side here is larger than the degree on the left-hand side here, and we get a contradiction. So I can say thus, f of x is a product of 2 smaller degree polynomials, Okay, so that takes care of our forward direction. Not too bad. So now let's clean this up and take care of the backward direction. Okay, so the backwards direction is kind of similar. So we're going to say, well, suppose f of x is a product of 2 smaller degree polynomials. In particular, we'll call them g and h, and we have the degree of g is less than the degree of f, and the degree of h is less than the degree of f. Well, since these have smaller degree, and their degrees have to add up to the degree of f, by necessity, we have to have that the degree of g of x is bigger than or equal to 1, and the degree of h of x is bigger than or equal to 1. But then neither g nor h are units, right? Because the units are the constant polynomials. So neither g of x nor h of x are units. So f of x is irreducible, or rather is reducible. And we're done. Right, the idea here being that f and g are not associates because h is not a unit, and f and h are not associates because g is not a unit. Okay, so we can consider 2 examples now. For example, the polynomial x squared plus 1 as an element of C bracket x is reducible according to our theorem. Why is it reducible? Well, x squared plus 1 can be rewritten as x minus I times x plus I, where I squared is equal to -1. All right, so this is an example of a reducible polynomial. If I try to do the same thing in R bracket x, we can show that this is irreducible. And this is actually a nice exercise to try. Show that x squared plus 1 is equal to ax plus b times cx plus d is impossible. if A, B, C, and D are elements of the real number. So it's actually a really nice exercise to try. We can show that x squared plus 1 is irreducible by showing that it can't be factored into smaller degree polynomials. Our only choices would be a polynomial of the form ax plus b times a polynomial of the form cx plus d. Okay, so we can show that x squared plus 1 is irreducible this way. Okay, and finally, we'll present two theorems whose proofs we'll omit. And the reason is that the proofs are identical to the proofs that we did for the integers. So they're actually good exercises to try. It's a good review of similar theorems that we had for the integers. Okay, so let's consider a polynomial p of x in f bracket x. Then the following are equivalent. 1, p of x is irreducible. 2, whenever p of x divides b of x times c of x, then p divides b or p divides c. And 3, if p of x is equal to r times s, then either r is a non-zero constant polynomial or s is a non-zero constant polynomial. And the idea here is this is similar to the property that we had for primes when we were dealing with prime integers. We said p is prime if and only if whenever p divides b times c, then p divides b or p divides c. If and only if p can be written as r times s, then either r is equal to plus or minus 1 or s is equal to plus or minus 1. Right? So that's the equivalent theorem, and the proof is identical. The second theorem is equivalent to the fundamental theorem of arithmetic. So on top of this, every polynomial can be uniquely expressed as a product of irreducibles. Just like for integers, we can express any integer as a product, or any non-zero integer as a product of primes in a unique way, right? So in what kind of unique way is this? Well, we'll say every non-zero constant polynomial in f bracket x is a product of irreducibles. And this product is unique in the sense that if I give you two factorizations, p1 times p2 times dot 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 times pr, and q1 all the way up to qs, and all the pi's are irreducible and all the qi's are irreducible, then r is equal to s, meaning there are the same number of terms here as there are on this side. And after reordering, each of these p's is an associate of each of these q's. So p1 is an associate of q1, p2 will be an associate of q2, all the way up to ps will be an associate of qs. And this is analogous to our statement when we did this for the integers. We said each pi was plus or minus each qi. And that was just saying that each of the primes on the left is an associate of each of the primes on the right. And again, I'll state that these are good exercises to try. It's a good way to go through and make sure you understood the proof the first time for integers, is to try to reproduce the same proofs for these two theorems. You'll see that the proofs are pretty much identical up to some terminology, but the idea is exactly the same. So we'll stop here.